just because we get lucky. The other thing you can do is you can try to deliberately make them cancel out. And so what we do there is we deliberately, so this is at sort of at the hardware level, we deliberately mess with the gates. So instead of applying an X gate, we apply the, oh, here I can show you. Say this is the circuit you want to apply. This is a dumb example, but I'll just show it. Say that's the circuit you wanted to apply. It is 4 X gates, which is trivial, of course, but so be it. Okay, so be it. Instead of applying that, what we do is we apply. Let's see, how does this work? Yeah, so I'll conjugate. I'll insert between each of these gates. I'll insert a pair of polygates that cancel out. PP, QQ, RR. So these are just polygates, and any polygate squares to the identity. And so overall, this circuit is the same as this circuit should have the same effect as the original circuit. Okay, and then what we do is we group them like this. Okay, so here I have P times X times Q, or I guess Q times X times P. So this gate then we compile into the hardware as one operation instead of 3 operations. So this is called twirling. And the idea of twirling is we work in random polybases, kind of, and it makes the errors sort of point in random directions intuitively. Like that's not rigorous, but there are some rigorous things you can say if you make strong assumptions. But roughly the idea is you don't want things to add up like this. Okay. Okay. All right, so this is obviously a huge area. Yeah.
So if we want to simulate the Hamiltonian using the unitary circuits, so can we transform the Hamiltonian noise to the previous noise?
Sorry, do you mean this or something else?
So if we use the circuits to simulate the Hamiltonian, like into the IHT.
Yeah.
Yeah. So can we transform the Hamiltonian noise to the unitary noise, like the discrete noise made of X, Y, Z?
I don't know. I think it's a complicated question, right? So the computer scientist answer would be, if you're trying to implement a Hamiltonian simulation, you just think of that as a logical operation like any other, and so you encode it like any other operation, and you do all the stuff like anything else. And so there's no difference. But if you're talking about how you do this in the near term with near-term hardware, then you could say maybe there's smarter things to do. In particular, yeah. So in particular, often, sometimes you have algorithms that are sort of inherently noise resistant, in the sense that, like, you think you're applying a certain gate, like a certain Hamiltonian for a certain amount of time. You're not applying that gate because there's some systematic noise that happens. But in fact, maybe it doesn't matter that you're not applying the gate as long as it's always the same thing. And like, because, well, like a concrete example, I guess, would be like if you're trying to prepare the ground state of a certain Hamiltonian, which is a pretty common problem. A typical way of doing it is you run a classical optimization procedure on top of, in order to choose the best quantum circuit. So your classical optimization procedure, it takes a set of parameters, and it outputs like your new set of parameters for the new set of gates. And the issue is, so the gates you think you're applying are not the gates you're actually applying. because of noise. But it doesn't matter as long as the classical as long as it's. I mean, you'll just get different parameters in the optimization. It'll still optimize. It's very strange.